So thank you for coming, everyone. Today we have Andrei BERNEVIG from Princeton University. So Andrei is a professor of physics at Princeton, and he did his PhD with Shucheng Zhang at Stanford University, where together they wrote a very large body of very influential work on the materials that have now become known as topological insulators. Since then, Andrei has gone on to produce several very large and impactful and really a voluminous body of work on topological phases of matter in all forms. And for this work, he's received several prizes and awards. He's a fellow of the American Physical Society and has been awarded the Europhysics Prize, the James C. McGrady Prize for New Materials, a Guggenheim Fellowship, and the New Horizons in Physics Prize, among many others. And one thing that I personally find very admirable about Andrei is that unlike many of the other big shots in this field, his group produces long, pedagogical, and well-documented papers, and that he can personally brawl with you on all the proofs and all the appendices, and he will. And this really sets the standard for reliability and reproducibility in this field. So, Andrei, go ahead.
Thank you so much. And, thank you for producing these long and comprehensive appendices, because obviously I couldn't do it. So thank you, Ben, for doing it. Today I wanted to give you a very, very broad, and by broad I mean extremely broad, presentation on kind of start off with topology and go to how you apply it to two-dimensional engineering, and really the focus at the end, although we'll be using very similar things that we've all done in topology for the past, I don't know, more than 18 years. What we'll be applying these concepts on are 2D Moire materials. So it's just a little bit of a different field, but all the concepts are coming from, a lot of the concepts are coming from topology. The only extra additions are maybe interacting fermions, but you'll see how to do this later, how topology comes in to give new states of matter. So basically, Moire patterns are things that happen when you put two periodic patterns together. So this is, let's see if this works. Oh, there was a video here which stopped working somehow between transfers of laptops. But if you take a pattern, a periodic pattern with some periodicity, another periodic pattern with the same periodicity, shift them a little bit, here's what happens. You get a new periodic pattern. Now, of course, as you know, you can get this in nature, in twisted bilayer graph, in twisted TMDs, and then in many twisted things. For example, parrots. Parrots have these in wings, and many other materials. And I'll show you at the end that you can basically create these type of Moire materials, plug and play. We now have many others, hundreds of possibilities for just 2D layers that are being exfoliated. Basically, almost every van der Waals material will be exfoliated. The issue is how large the flake is, but right now we've gone beyond TMDs, and you can exfoliate single layers, and then the possibilities are endless, because you can take homo bilayers, hetero bilayers, you can twist the angle to create any type of angle, and then you have an infinite phase space to play around with. So let me start. So obviously what we do is condensed matter physics, and we're looking at quantum states of matter in this talk. So the way we start analyzing quantum states of matter, and really the building block of everything, is this beautiful non-interacting electron. Without non-interacting electrons, you couldn't do anything. And the non-interacting electrons, many people in the last century, at the end of it, were thinking about high TC, etc., and we're basically saying non-interacting electrons are dead. But non-interacting electrons really have provided the first picture of materials by providing Bloch's theorem and by arranging the electron bands in as a function of momentum in crystals. So if you have periodicity, this is where the momentum of the electron lives. It lives in a area of momentum called the Brion zone, or the first Brion zone, which means that an electron with momentum outside of this Brion zone has the same energy as an electron with momentum in this Brion zone by translation by 2 pi over some lattice constant. And this is the band diagram of silicon. These are the allowed energy levels. This is the band gap of silicon. And this band gap engineering is at the basis, for example, in gallium arsenide, of all of your chips that you have in your computer. So it's a very powerful concept that takes into account the energies of the electron. Now, when you add interactions, of course, because of this entanglement, you have exponential challenges, because this single electron picture basically allows you to say that the state of many electrons is just a product or a Slater determinant state of the single electron particles, which basically means that the quadratic Hamiltonian, i.e. energy Hamiltonian times the creation operator times the annihilation operator of the electron, doesn't scatter between different energy states in this momentum space, is diagonal, right? So when you add interactions, that's no longer true, and then all the states, it's not always true. You can have Krylov subspaces, but in general, all the states scatter into each other. So if I have n spins or n electrons that are tight to the sides, and this electron can have spin up and down, etc., you immediately have 2 to the n states, and when you add interaction, they all scatter into each other, and then you're basically done. You cannot diagonalize this Hamiltonian for n, for example, greater than 20, for n greater than, 50. This means you have more number of states for 50 particles than the number of particles in the universe, so you can't hope to do it on a classical computer, at least. Okay? So that's the approach we'll be taking. First, take the non-interacting electron, then try to add interactions, and try to kind of beat this exponential wall. Beating this exponential wall invariably tells you that you must do some sort of a unitary transformation to get to the relevant excitation. Since most of these states, are going to be at high energies, all you want is some unitary transformation to get to the low energy states. Usually for Fermi liquids, for example, that unitary transformation is called quasi-particle. For other things, as we'll show you, is called something else. But the strategy is always the same. You go first to the non-interacting electrons, and then the non-interacting electrons have 2 things that are important about them. First of all, the dispersion, i.e. the energy versus momentum, which is shown in the previous slide as the dispersion of silicon. Here, we'll just show the dispersion of graphene, which is a hexagonal arrangement of atoms, of carbon atoms, and these bands come from the pz orbitals of carbon, and the arrangement of these atoms basically gives you this Dirac structure at 2 inequivalent points in the momentum space of the electron, the allowed momentum space, i.e. the Brion zone. This is K and this is K prime. We'll also call them valleys later on, but the moral of the story is that you have a high velocity, about 10 to the minus 2 the speed of light, so still very high for condensed matter, high velocity electron, and the Hamiltonian here looks exactly like the Dirac Hamiltonian, 2-dimensional Dirac Hamiltonian that high energy physicists know. Now, this high velocity tells you that by the time you reach, 10%, a very small amount of deviation from the K point from this particular point in the Brion zone, by the time you reach 10% of it, you've gone to 1 or 2 electron volts, okay? Because it has such a high velocity. So the large bandwidth electrons, low density of states here, that's the energy. But also, there's another thing in the Schrödinger equation for electrons that you must take into account, and this is where people in the late 80s and 90s who were basically saying single particle electron theory is dead. That's where they were mistaken. That, of course, the Schrödinger equation has the wave function, and this is very important for everything about that is done to characterize single particle electrons, and by default, then there are many body states. And this wave function, the reason why it's important is because wave functions depend on momentum. So you're solving Schrödinger equation the Hamiltonian at momentum k, which I've argued is diagonal, at least in single particle, times the wave function equals energy at momentum k times the wave function. And for example, for two orbitals, then this wave function is really a map. Why? Well, I said that the momentum is periodic mod 2 pi in one direction and the other, so the space of momentum is a torus, but then the space of the wave function is also a manifold. So it's very easy to understand this because the wave function really, for example, in this case where it's an S2, usually it's the manifold you need to determine what it is, without any symmetries, it's some complex projective plane. But for this case, which I envision here, which is just two orbitals, so I have on site, for example, my electron can sit in an S and a P orbital, and then I have many sites with many hoppings between the sites or many interactions or many probabilities of going from one side to the other. Then the wave function is just a two-component which gives you the probability of the electron to be on the S or the P orbital, okay? And you can immediately see that it has to be normalized. This is complex, this is complex. The normalization would give you two complex numbers squaring their absolute value to 1, so this would be 4 real numbers squared to 1. It's an S3, it's a 3-sphere, but there I said it's an S2. So why is it an S2? Well, the Schrodinger's equation H psi is equal to E psi is invariant under gauge transformations, and I can make a gauge transformation here where I can make at least one of these real, and at most one of these generically real. So I can make this real by basically unwinding the phase of this. So then I have one real parameter, two real parameters, which square to 1, and that's an S2. And this is the simplest case for two orbitals of a map that you can have. And basically, then if you realize your wave function is given by maps, then you know maps have invariants. And these invariants are topological, and which means that basically you cannot get between them by making small transformations. And that tells you that you cannot do adiabatic transformations between wave functions that are in different classes. So this type of understanding that wave functions are really maps basically gives you almost all the, well, not the math obviously, but all the physical insight into the simplest type of topology, which is the one that you need no other symmetries for, no time reversal, etc. So let's go through it really quickly. How do I know that there's several types of, for example, of such maps? Well, you can kind of see them already. One map is where my S orbital, for example, has an energy which is minus infinity times the S orbital. Okay, this corresponds to a wave function that is just 1, 0, because the electron always likes to sit in this orbital, no matter which momentum it is or which site it is. It always likes to sit in the orbital of, if I have one electron per site, of infinite energy to gain it, and that means that the wave function does not wind, it just stays at the North Pole. Okay, now I can add a little bit of winding of this wave function, so I can add here some delta k, and then I can add some normalization, I can add some small change, okay? And that means that this guy, this vector here, will move around the sphere a little bit, but it will not cover the entire sphere. So everything that doesn't cover the entire sphere, as the momentum goes in the Briand zone on this torus, we call wave function of topological invariant 0, and then you can have wave functions that cover the entire sphere 1 time, 2 times, 3 times, 4 times, etc. N times. So this is a Z topological invariant. Here's one that covers it once, for example, as the momentum goes into the Briand zone. And if it covers the entire sphere once, then we call this topological invariant, wave function of topological invariant 1. This would actually be a Chern number, really, in the end. But the moral of the story is that you cannot get between these two numbers with small changes of whatever Hamiltonian you were solving here in Schrodinger's equation, because in order to get between two integers by small changes, you're going to spend an infinite amount of time. So that gives you a physical principle that if I have a material like the silicon before, which actually is described by such an integer which is 0, and some other material described by an integer which is 1, then what I would necessarily have, as I would kind of take the parameters of this material whose wave function is described, covers this, for example, this space once or twice or non-zero times, and I would try to tweak the parameters to go towards this material which covers it 0. Then I would invariably have to have, if these materials are insulators, i.e. if there's no electrons at the Fermi level in this material or in this material, so there's no electrons at the Fermi level, it's kind of like that silicon that I was showing you before. If these are the allowed energy levels, the Fermi level is here. So if I put one of these materials that looks like this close to another one who in energy can also look like this, very similar, their energy spectrum can be, this is energy versus momentum, their energy spectrum can be very similar, but the wave functions can be very different, then invariably, because I cannot go between these two by small changes, no matter how I change, so I put this in a region of space, I put this other one in another region of space, at the edge I must have something crossing the Fermi level, edge states crossing the Fermi level, and that means the breakdown in the adiabaticity, and that's how you basically change this topological invariant by edge states. So there you know everything that needs to be known so far about the simplest example of topology. You have wave functions that are maps, they're described by integers. Anything that's integer non-zero, when you put it to an integer 0 wave function, if it's an insulator, you're going to get a region of gapless edge states, i.e. you cannot go from one to another without closing the gap. Now there's another corollary, which is a little bit more subtle, which basically tells you that any insulator that's described by a wave function of topological invariant 1 cannot be described by exponentially localized wave functions. Why? Well, for example, if I have integer 0, which I said integer 0 is just wave function of integer 0, this is just this Hamiltonian, the North Pole, then you can immediately see I can have delta functions. My electron sits on the s orbital, this is just an s orbital being completely localized, and the electron just sits there. That's a delta function. Okay, that's exponentially localized. But the moral of the story is that if you're exponentially localized, then you can only have this atomic, this winding number be 0, okay? Because I can always squeeze the localization a little bit or a little bit more and make it basically this delta function localization, and you can always have it to be 0. Hence, this side, which doesn't have topological invariant 0, cannot be expressed in terms of just purely exponentially localized states in, hand-waving argument. But these hand-waving arguments actually turn out to be correct. Okay, so that tells you that topology is important, and indeed it is. So this are, for example, this is a quantum Hall effect where, because of these edge states, you get quantization of the whole conductance, i.e. the current injected in the x direction over the voltage measured in the y direction, etc., to better than 10 to the minus 13. And I would challenge any of you, well, any of the people that don't know the experiment, obviously, to say that in such a sample, which looks like it's been soldered by some careless person, although they were very careful back in the days, you can get quantization 10 to the minus 13, which really replaced, right, the e squared over h metric, I guess, which is held in Paris or somewhere. So then this is the photonic crystal. You can see if, this is not a fermionic system, this is a bosonic system, but you can see that you're sitting here in a light band gap. There's a band gap for light, but then because of this type of topology, you can see you have edge states at the edge of the sample, and you can get more things. Now, the only thing that changes, so this is, topology, and this is what basically single electron particle physics missed in the last century. And the only thing that changes when you add symmetries is the fact that this manifold becomes now an orbifold, I guess it's called, which basically tells you that some points K are special, okay? Because the reason, the reason why they're special is because you impose symmetries such as time reversal, so then the K equals 0 point is invariant under time reversal, and you just get different spaces. And you can classify these things nowadays by just some websites. Let's see if this works. Okay? So for example, what you do is, and this provides a classification for compounds. So what you do is you go on this website that was actually made by us, including Ben, but you just go on this website and instead of taking elements, you take materials. So you just plug in some materials and you go here and you see an integer, okay? Now invariably this is actually a system of topological invariants. So these are the topological invariants, they're just integers. This is a system of topological invariant 2, which is one of these, well, it's not the one that Sophie Guérin and Hélène Bouchard looked at. They looked at bismuth and bismuth bromide in their group, but it's got the same topological invariance. So it's a higher order topological insulator. To understand all that, you need to read what Ben was talking about of 100 pages papers, but by now these are tabulated. Okay, so you don't really need to read them. You can just go to the Bilbao crystallographic server. If you have the DFT, you can just plug in your DFT wave functions, or if you're better, DMFT even, if you can just plug in the wave functions once you have them and get to these topological invariants, and what they are. If you read again several 100-page papers, but again, this is all tabulated now, so you can just get the results by typing in some command prompts or more command prompts. Now, what I have to tell you, so there's two things I have to tell you. So first of all, this type of work basically involves classifying hundreds of thousands of compounds, so it takes a lot of time, and the reason why it takes a lot of time is that there's a lot of symmetry groups in nature. So crystals can show up in 1651 magnetic symmetry groups. Each of them you have to classify the topology for each of them, and this is what we did in this paper, which I don't know how many 100 and something pages, but basically it classifies. Of course, you don't put all the information, most of the information is actually on the website, but basically this magnetic topological quantum chemistry classifies all these indices for any magnetic group. Now, what I have to tell you is that even this classification is not complete because it requires some symmetry of the symmetry group, and you need there's systems that can have topology without symmetry, and this is actually what's being worked here by Ben and Ben's group. But basically, there is even a more complete classification, which we hope, I guess Ben hopes to have done by October, maybe. So we'll see. Okay, but the moral of the story is that at least now we know how to classify electronic wave functions to single particle functions to some extent. But the wave function is not the entire thing, the single particle wave function. Even in single particle, as I said, the other thing is the energy of the system. And the energy of the system, or of the single particle electron, is very important. And there are cases which have basically been also missed by original band theory, which I'm going to present now. So we know that the way you get dispersion, i.e. non-zero energy versus momentum, so this is, for example, a 1D system of sites of electrons sitting here, and then the electron has a probability of hopping from this site to this site. This probability, is there more chalk by any chance? Or, because I found only this small piece, which I'm going to write with my nail very soon. So that probability of the electron of hopping from one site to another, those are sites, but that probability is really just overlap of orbitals. Oh, thank you so much. Oh, thanks. Oh, great, thanks. So if you have a p orbital, for example, and another p orbital For example, there's some, overlap, and you get the wave function on this side, grad squared, the wave function on this side, integrated over the space. That's a number. It's called hopping amplitude. Here it's given to be 1 in some units. Okay. Obviously, it decays. So if I take the hopping of this side to this side, right? This is angstrom size. This is also angstrom size. But the more you get to two sides, etc., just because the wave function of the orbitals, right? This is just the atomic wave function. The wave function, this is the grad squared over 2m of the electron. The wave function of the orbital decays exponentially. Then the hoppings are basically decaying exponentially. So this is the power of kind of these hopping models. You don't need to take into account several of them for these models. And then you immediately see why you get dispersion. If I have a hopping of 1 here, then if I Fourier transform, there's a probability exponential to the ik of the electron going from here to here, and exponential to minus ik from here to here. You add them up, you get a cosine dispersion. That's it. Now, there's a way of making this band not have dispersion, and that's to kill this coefficient here, which here is 1, but I can make it t, which is this integral, and I can just kill it by, for example, say you are God or whatever you believe in, and stretch the lattice constant to infinity. Then, of course, since the orbitals are exponentially decaying, you are going to get this to be very small. That's called an atomic limit. Why? Because then I'm just going to have sites that are far away. And that corresponds to this type of situation where I have sites that are far away that sit in kind of quantum wells meaning the atoms, and don't hop to each other. And that gives you a band dispersion that looks like this. But there's another type of flat band dispersion, meaning very little dispersion, which you can see, for example, in this material. Okay, and this is the DFT of this material. I'm not claiming that the DFT is correct, so if you know something about this material and find the DFT incorrect, then it's not my fault. But the moral of the story is that this material has, if you look at this band structure from DFT, regions of flat bands and then large dispersive bands. Okay, and the way you know this is that these are some momentum axis in the Brion zone. And it's got flat band, and now you start with a dispersive band. And this dispersion is huge. It's 3 electron volts, right? It's pretty large. And the reason for these flat bands is really this material looks like a special lattice. It's called the Lieb lattice for, it's a bipartite lattice with 3 oxygen and a tungsten, okay? And these lattices have flat bands because of quantum interference, basically. The wave function can hop, and you know that it can hop because the amplitude is not 0. How do you know it's not 0? Well, you know that in some directions in momentum space, it has dispersion, so it cannot be 0. But in some other directions, it doesn't have dispersion. So for those directions, there's some cancellation of signs when the electron hops around and comes back, for example. There's some cancellation of signs, even though the hopping amplitude is non-zero, and it's really of the order 3 to 5 electron volts, huge, or more. But for those directions, it's 0 because of quantum interference. And that happens on a Kagome lattice, etc. So that happens in realistic materials. But the problem with realistic materials is the following. So you try to do this in realistic materials. And why do you try to get flat bands in realistic materials? Well, you want interactions. You want to for example, understand interactions or find materials where you have interactions. And if you quench the kinetic energy, i.e. make a flat band, then interactions are going to be the most important thing. So people have been trying to look at flat bands. There's also, there's a lot of confusion in the literature. There's, a lot of whether flat bands are good, bad for superconductivity. In the end, in 3 dimensions, I think they're bad just because the Coulomb interaction will just ferromagnetize them. But if you could tune the interaction to be purely attractive, flat bands would have much higher superconducting temperature than normal dispersive bands, for reasons that we can go through. They are very easy. But the moral of this slide is to show you that flat bands exist in nature. For example, this is one of the Kagome materials, and you can see clearly that it's got some very flat bands at the Fermi level. By very flat meaning 100 milli-electron volts dispersion, etc., which is very little in a material of, bandwidth 8, electron volts, or etc., from, for example, from here to here. This is a huge bandwidth, but there's some very flat bands. These come from the Kagome lattice. They are, but the unfortunate thing is that if you want to do some experiments in these flat bands, which people do, you can get something interesting, i.e., say, non-Fermi liquid resistivity, or some interacting effects, or some Heavy-fermion looking physics, but you can't pin it down. The reason, and that's why a lot of these papers that have this physics, there's a lot of confusion of where the physics is coming from. I mean, people know that it should be coming from a flat band, but the problem is you have a lot of other dispersive bands around, and that's just chemistry, because in this material, for example, you have 3 nickels per unit cell, right? That's why it's Ni3. Each nickel has d orbitals. There's 5 d orbitals times spin. That's 10. Times 3 nickels. That's 30 orbitals, which is the reason why you have, and then there's indium, and that's just the d shell. And then there's indium, okay? So that's the reason why you have so many bands. The number of orbitals is equal to the number of bands. And you can see you have this flat band, but then you have all of these dispersive bands around it. So the problem with chemistry is that it's, you just have too many orbitals. Of course, and the bands, there's a spaghetti of bands. Of course, what people are trying to do, including Ben and others, are trying to, and us, we're trying to basically find kind of the needle in the haystack materials that are very clean. But in general, they're going to be looking like this, and there's a lot of work to do to get rid of these, the behavior, or to understand, to separate just the flat band and understand the behavior of the flat band. Now, that type of thing is easier in Moire lattices, and the reason for it is controllability. So Moire lattices have several advantages. They also have several disadvantages. The disadvantages are the length scales and the fact that you're going to be having much less density of electrons than in a material chemistry situation. The advantage is controllability and doping that you can do without adding impurities. So this is a Moire lattice, which is just a twisted layer, 2 layers of graphene, for example, in this case. And you can clearly see here the graphene lattice, but you can see a superstructure that has appeared on top of it. This superstructure shows basically what you would see if I didn't show you these smaller sublattices, smaller initial lattices, right? The small hexagons are just the graphene carbon hexagons. These are the superlattices. You'd say that these are new orbitals or new degrees of freedom, right? If I just showed you a picture without showing you it. But these degrees of freedom really are made of thousands. This is a larger angle, but it's 1 degree. They're made of 10,000 carbon atoms or electrons of the carbon atoms. So effective degrees of freedom, the length scale is around 20 or 10 to 20 nanometers, okay, which really puts them in between cold atoms and material chemistry. But unlike cold atoms, these can have larger interactions. And unlike material chemistry, these can have larger controllability. Now, what we'd like to actually do is be able to control material chemistry as well as we control this, and then you'd have high density and controllability, which is really what you want in the end for things like, high temperature superconductivity, etc. But so far, we're going to focus on this. So here's what happens, and if in such a lattice. In such a lattice, so take graphene. Remember, our graphene are carbon atoms with a bandwidth of, for example, if we go all the way here, 6 electron volts. So it's a large bandwidth. Our Dirac electrons that are very dispersive. Take 2 layers and twist them by an angle, which you can see how small it is here, between 0.8 and 1.3 degrees. Just tiny. Now, in single layer graphene, people have been trying to, induce interactions without a magnetic field. If you add the magnetic field, the bands become flat, Landau levels, other physics. But without a magnetic field, people have been trying to observe interacting effects, and there are none. The reason for this is the low density of states of a Dirac electron, which is 0, because, exactly at the touching point, I have 2 states, really. So 0 in the thermodynamic limit when you divide by the area. Now, notice what happens as you decrease the angle. So at large angle, it looks, when I take two layers and twist them by this angle, at large angle, which is coming up now, it basically looks like this Dirac nose. This is one of them, and this other one was there, right? So it looks like nothing happens. But as you twist the angle to 1.05 degree, which is called the magic angle, this bandwidth has now become less than 5 milli-electron volts. This is the non-interacting band structure. That's a 1,000-fold decrease in the bandwidth from 6 electron volts to less than 5 milli-electron volts by just twisting by a small angle. In fact, the way the band structure looks is like this, and this is called the Bistritzer-McDonald model. The band structure of looks is like this. This Brillouin zone is in the new periodicity of the Moire lattice. So these momentas, right? The Brillouin zone is 2 pi over the unit cell. So the unit cell is much larger, hence these momentas are much smaller than in graphene. But nonetheless, I can still plot the band structure here for reasons that I can tell you. And you can see what happens here. You have two very flat bands at 1.5 degrees, two very flat bands. But in order to do the proper counting, we must remember that graphene has these two values, K and K prime, so we multiply it by another 2. It also has spin with no spin-orbit coupling. Carbon atoms have 40 microelectron volt spin-orbit coupling, so we multiply it by another 2. So you have 2 times 2 times 2, that's 8 bands here. So I can fill them with 8 electrons per Moire unit cell. So we're going to count the filling in this gap. We're going to say it's minus 4 electrons. In this gap, we're going to say it's 4 electrons. So from here to here, I can add 8 electrons. Charge neutrality, the reason why we want to count it like this, charge neutrality, i.e. Fermi level 0, we're going to say it's 0 electrons. It's just a way of counting it. Now, why is this good for people that don't do condensed matter? How is this more how is this better than material chemistry? Well, here, in order to put electrons from here to here, I need 8 electrons. So to populate these flat bands, or I can put, minus 3, minus 2, minus 1. Okay, now that's electrons per Moire unit cell. The Moire unit cell contains 10,000 carbon atoms, 10,000 original unit cells. So really, this is a very small doping at the original graphene lattice. Normally, you cannot dope a material with 1 electron per unit cell, or 2 electrons per unit cell, or even 0.5, 1 electron per 2 unit cells. There's just too much charge. If you dope it by an electric field, you need a huge electric field that first of all, you break down the material to dope that, to change the chemical potential, if you do it at the angstrom scale. So people in material chemistry, they use chemical doping, but that changes the properties of the material. So really what you want to do, just like in the quantum Hall effect, to keep the system clean, is you want to change its doping by an electric field, or its Fermi level by an electric field, and then the moral of the story is that you're stuck with small changes of electron number. But because this unit cell is so large in the Moire, you saw how the unit cell becomes large, then you can induce an integer number of electrons, or you can add a large number of electrons per this Moire cell, because 1 electron per Moire cell means 1 electron per 10,000 original graphene cells, and that's not hard to do. So now what happens here is that if I go between minus 4 electrons and 4 electrons, so I start, doping, I can do it continuously with a gate, then let's just look at these bands. I can go, say, minus 3 electrons. At minus 3 electrons, I've doped it with 1 electron with respect to this gap, and then I'm here. And then the system would be a metal. It would intersect electronic states. In non-interacting physics, it would be a metal. Now you go to minus 2, even more, you raise the Fermi, it would be a metal everywhere. But look what happens, and this is data from DMFT's group, look what happens in reality. What happens in reality is that as you change the filling from minus 4 to 0 to 4, at integer, so at minus 4 and 4, I have single particle gaps, meaning regions of no electronic states. But in between, in single particle, I should have a metal. Now, you can see the resistivity. This is the resistivity shooting up at integer fillings. For example, minus 2, 2, it shoots up. So resistivity shooting up, highly resistive, means it becomes an insulator. You can moreover see resistivity going to 0 in between these, right? So when I'm at integer filling, I have insulators. When I'm in between them, resistivity goes to 0. It's a superconductor. Okay, so you can see that clearly now this phase diagram doesn't match the single particle phase diagram, which would just be a metal everywhere. And this is due to many body effects. So we knew that many body effects would be important. Why? Because we've quenched the kinetic energy of these electrons. They have no kinetic energy. All they have is interactions, and actually interactions are larger than the bandwidth by a factor of 3 or 4 in this case. So now you have a highly interacting electronic system, and you ask, how can I describe it? And now the next slide is going to be simple, but the next 2 slides are going to be more complicated for the condensed matter people, and then we'll go back to more simple stuff. So how do you basically model such a system? Well, first of all, you could say these flat bands are flat just because, you know, I don't have any hopping and everything sits in a quantum well. And that would give you, that would give you a system of electrons that are just quantum dots localized. But you know that there's no localization here, at least no full localization, because you'd get superconductors. So you get phase coherence and everything goes around and moves. But if I was looking at, the picture given by STM, these are just like quantum snapshots of the electronic structure. This is the Moire unit cell. You can kind of see here, if you look you can see an internal structure. That's the graphene lattice. You can clearly see some dots. There's the initial graphene lattice. But this is the Moire scale. So the initial graphene lattice is angstrom size. This is nanometers. Okay, so about 10,000 or 8,000 initial unit cells in basically this unit cell here. Okay, so this is the Moire charge density. But if you were to see this, you say, oh, the system is very localized, right? It sits everywhere. But you know that there cannot be full localization because, okay, we see insulators, but we also see superconductors. And there's many other things that we see, such as churn insulators, etc. So a very famous paper in the field said the following: the correlated state features an unusual combination of contradictory properties, some associated with itinerant electrons and some associated with localized moment. So, the experimentalists like to present it as somewhere in between localized and topological. That somewhere in between doesn't really exist. The bands are actually topological, but they're topological in an interesting way. So what do you do? How do you express this? So it cannot be fully localized, okay, because you have superconductors, so that we know. And the charge density looks like it's fully localized. So what's going on? Well, first thing that you know is you take this Bicester-McDonald band structure and you play the game that Ben, Barry, Jen, and all of us played for the past 10 years. And you look at the properties of these flat bands. There's 8 of them, but per spin, there's 2 of them. Okay? So you look, and these are good quantum numbers per value. So you look at these flat bands in the non-interacting picture. And the first thing you do is you establish their topological properties. And these can be established in many ways, actually. It turns out that there's a stable kind of topology here that's given by the Wilson loop. But there's a simpler way if you want to understand the basic levels of the topology, is you just get the high symmetry point eigenvalues, you plug them in the Bilbao crystallographic server, it gives you an index, a topological index that's non-zero. It's basically this type of eigenvalues can never be described by an atomic limit. So now we know that these bands are topological, and remember what I said at the beginning, topological bands cannot be described by exponentially localized von orbitals. Okay? But we also know by experiment that, it looks pretty localized. So what's happening? Well, what you can do is you can build orbitals that are localized at the triangular sites of the Moire. So the Moire has hexagonal lattice, but you can build localized orbitals at the triangular sites, which is exactly where those dots, where those large dots look. These are effective orbitals. They're made of thousands of carbon atoms. You can write them down as some envelope functions. And then you can ask 2 orbitals per unit cell their symmetry, even though I'll call them F electrons for abuse of language, are px plus minus IPY. And these orbitals give you the same eigenvalues at the k point, at the m point. They give you different eigenvalues at the gamma point, but the gamma as the flat bands. But in fact, they give you the same eigenvalues of these remote bands, which are within the reach of the Coulomb interaction. So then you ask, how much of these super localized orbitals are contained in these bands? Now, at the gamma point in these flat bands, you cannot have any of them. By symmetry, they have the wrong symmetry. But the sooner you go away from the gamma point, you find that these bands are mostly localized orbitals. So 95% of this flat band is given by these localized orbitals. So this is like a system that has become topological, these bands, for people that know topology, by a very sharp band inversion just around some point. Although it's always topological, so there's no band inversion. But you can clearly see all the Berry curvature should be actually localized somewhere here, because all of this is trivial. So then you say, okay, 95% of this is trivial. We can build Wannier orbitals. This is by doing Wannier 90, you can get some localization. It's 0.2 of the unit cell. In fact, there's zero hopping between these two F orbitals by abuse of language. Between here and here, there's zero hopping. So these are just localized orbitals. But we know there's superconductivity, etc. This system cannot be made out of localized orbitals. So there's got to be a chain, there's got to be some delocalized state. And in fact, you can deduce what the delocalized state is. The delocalized state is the one that carries the topology and is given by an AB untwisted, we call it C electron because it's just the conduction electron, the one that does all the conduction. So it's a untwisted C electron, AB, and you know that this has a double vortex here. Okay, and this double vortex is topological. This is topological semi-metal. You cannot break this double vortex without killing some of the symmetries of the system. So this topology, the topology of the bands, has now been pawned off on the topology of the dispersive fermion. So you can ask, well, how does, if I combine these two together, how does it look? Well, the first combination is where I don't have them hybridize, i.e. there's no mixing between these electrons here, which sit on the triangular lattice, and these conduction electrons which sit in between the triangular sites. And then you'll have a band dispersion. These guys, these F electrons, which are red, they'll just stay flat in energy. This is momentum, this is energy. They'll just stay flat in energy because they're just localized at the triangular sites. Then there's this double vortex. It looks like this. Now you can say this doesn't look very much like what you showed me before. The only thing that you need to do, well, this is not, you're not putting it by hand, you're deducing it. Because these double vortex here and the F electrons have the same representation at the gamma point for condensed matter physicists, there's just a constant hybridization between them, and then bada bing bada boom, the bands become exactly these. So the red are our model, and the lines are the Bicester-McDonald model. So you can match these bands, and this is a 6x6 model. This is a much larger model, so you can match this band structure exactly. So now, what we have done, how many more minutes do I have? I think. Okay, maybe like I take 5 more. Okay, or 6 more. So why do we make this? Why did I say that we're going to make this flat electrons, conductive electrons? This is really just a basis change. You see, we can, at least at low energies, the Coulomb interaction is of the order 30, 40 milli-electron volts, 50. It can only get you from here to here within this energy range. I'm not going to match things at high energies. The experiment is not at high energies. But this is a good unitary transformation at low energies. It's actually almost perfect at low energies. So why is it important? As I said at the beginning, most of the interacting physics we can do is just changing bases because we can't solve it exactly. And this is a particularly good base to change. The reason for it is that most of the Coulomb interaction is now carried by the localized particles, which are the F electrons. So this is a Anderson model when you add interactions, and you don't add them by hand. Nothing here is added by hand. You just take the ab initio structure, you just compute these envelope functions analytically, then you project the ab initio structure onto these wave functions, and then you project the Coulomb interaction onto these wave functions, and you get some numbers. These numbers are obtained numerically. Now we can also obtain them analytically with some approximation, but the form of the Hamiltonian, the actual terms in the Hamiltonian, everything else is obtained analytically. So we're not guessing anything. We're not putting anything by hand. So indeed, you take the Coulomb interaction, which is some screened interactions because you have a metallic gate, and the screened interaction, when you project it into this F electron and C electron basis, that gives you these flat bands. So as I said here, okay, most of the band is F electron. You can see it here. Most of the band is F electron, but around the gamma point, it's the C electron. So you take this, you project it, you get to a Hubbard-U interaction in the F electrons, and this is the largest interaction in the model. So your model has become that of some heavy fermions with a Hubbard-U interaction coupled, and up to now it would be the same as the Anderson model, as the old Anderson model. The only distinct thing is that the conduction electron, unlike in the Anderson model, is topological, meaning it's got this double vortex here. So you can analyze, obviously, this is an Anderson model, it cannot be solved exactly, but what you can do is solve it exactly, for example, in the zero hybridization case, meaning the case where there's little hybridization between the F bands and the C electrons. There, you can actually solve it exactly and then add the hybridization as a perturbation. So I can solve it exactly. Well, remember I had these F electrons and this double vortex. Okay? This double vortex, I said, is enforced by topology, but now these F electrons have a Hubbard-U interaction. Because they have a Hubbard-U interaction, they don't like to sit at the Fermi level. So let's say I'm at filling 0, at charge neutrality. At charge neutrality, what I'll do is I'll try to fill these F electrons, okay, and move them away from charge neutrality, because if I fill them, I'm going to get an energy saving of U. Okay, so I'd like to fill them. My Fermi level is here. So these are called Mott-Hubbard bands, obviously for condensed matter physicists, they know they're called Mott-Hubbard bands. It's just that an interacting system with a flat band at the Fermi level doesn't like to sit at the Fermi level because it can lower its energy by moving the electrons down and up. Okay, so I move the F electrons here and here. These are now Hubbard bands. And you can notice that because you have topology, unlike in a Mott insulator where these would just this would become an insulator, because you cannot gap this. This is a Mott kind of a semi-metal. So you have Hubbard bands, but you have a semi-metal which stays topological. So then this is just an approximation that you just get by putting zero hybridization between the F and C electrons. But then what you can do is full DMFT, which has been done by the groups of Giorgio Sangiovanni, Tim Welling, Rosa Valentli, and Antoine Georges. So basically what you do is you actually treat the system, you get the self-energy, so you can get lifetimes, etc., in the approximation of the self-energy being K-independent. And this is a spectral function that you get. Okay, I'm going to take out these remote bands, replot this. This is a replot of this. And notice how different this is from the non-interacting band structure. Non-interacting band structure, this was the K point, this was the gamma point, this was the M point. This is the other K point, or the same K point, doesn't matter. But the non-interacting band structure was gapless, i.e. the bands came together at the K point, gapped here. You see there's a difference between at the gamma point, gapless at the M point, and gapless, or almost gapless at the M point, and gapless at the K point. Whereas this spectral function, just because the F electrons has now split by an interacting effect, is gapped at the K point by a large gap of the order Hubbard-U, gapless at the gamma point. Okay, so exactly the opposite of this. So now what does this say? This says that if you build two samples, okay, one at angle 1.5 degrees where you don't have flat bands, and one at angle 1.05 degrees where you have these flat bands and the interaction, the spectral function of one of them should look like this. At large angle, i.e. non-interacting, at small angle it should look like this. And you can just tune through this Mott transition, for example, by angle. Now, how do we measure such spectral functions? Well, there is a new type of that's a machine that's being pioneered by Charles Nani, but now also exists in Dima Efetov's group, that basically is like STM, but with momentum resolution. So what you do for the, for people that are not condensed matter, people that are condensed matter know it, instead of having an STM tip, which, is not, it's dirty, or not dirty, but it's not atomistically flat for large distances. This is like a tip that's flat for microns, okay? And I think it's a few, or maybe 500 nanometers, something like this, okay? So you tunnel coherently, and the tip and the sample is the TBG sample, okay? But the tip is coherent tunneling over 500 nanometers. And then you get momentum resolution also by just Fourier transforming. And what I can tell you, so the paper is not published, but you can see the talk at the Flatiron, or contextual hull for his data. At large angle, the spectral function looks non-interacting, but at low angle, i.e. at the magic angle, it looks like this. This is the K point, this is the L point. And you can see how even the energy scales match, or you can't see because I haven't showed them here, but this energy scale is roughly some renormalized U of the order of 40, 35 electron volts. This is exactly right on the money. So this looks exactly like this function. So now, hopefully, these, I can convince you that these are simulators of heavy-fermion systems, which you can go through the Mott transition. Last couple of slides that I wanted to show you is new things in this field. Now we go back to basics. This is the quantum Hall effect. This is that sample that I showed you is very dirty. It's got a topological invariant. This topological invariant reflects in the whole conductance, but if you go and fractionally fill a Landau level, you can get fractional Hall conductance, the whole resistance. 1 over it is the whole conductance. So you see 1/3, etc. This is the famous Stromer-Tsui Gossard experiment, etc. So you can clearly see the magnetic field that's needed for these experiments. So now you can ask, can I have this state at zero field? And in fact, it's been done. This also is due to twisting. Due to twisting, you can get bands that are flat, so interactions are important. So just like Landau levels are flat, but unlike in stoichiometric samples, you can put a gate and control the doping and fractionally fill these flat Moire bands. And what you get, you can see the whole resistance here at zero field. They put some field, which is very small to orient domain walls, but at zero field, you can see you get whole resistance of 3/2, i.e. whole conductance of 2/3. This is the 2/3 Laughlin state here, which has, it's just a material, no magnetic field, whole conductance of 2/3. Okay, so there's other things such as superconductivity and twisted WSE2, which I won't go through, but this is hopefully some quantum simulator for Luttinger-Kohn. And the last thing that I wanted to show you before I close, because I think I'm running out of time, is the fact that this is just the beginning. So the reason why this is just the beginning is the following. So far, all these twisted samples were just made to be twisted at the K point. So for example, graphene had the K point that then I twist. MOT2 actually also had the K point, but its band structure is actually gapped, but it's also the K point. Graphene had no spin-orbit coupling. MOT2 had Ising spin-orbit coupling. But if you want to put some order into what you twist, you basically have to realize that really, number one, the only thing you can twist and have theoretical predictions are clean band structure. And that's why people have twisted tungsten ditelluride. Okay, something who has twisted tungsten ditelluride. The theory there is useless because the band structure that you start off in monolayer is too complicated. So then when you twist, it's just going to be even more complicated. So that's why, I mean, the results are nice, but the theory, there's no way to predict things. Now, for things that look simple in the monolayer, then things you might have some hope of predicting the band structure in the twisted samples. And then you can put some order. You can ask, where do I want my monolayer band edge to be? At the K point, but there's also M point, there's also gamma point, etc. There's different lattices, There's with or without spin orbital coupling, so you can make about 37 classes of this. Now, to show you that this is not just the classification, these are crystals grown by Claudia Felser and Leslie Shoup and Emilia Morochan's group, which are now in the Effetov and Kinfei Mac labs, and they're very clean, and they weren't exfoliated before, but you put them in the labs and you can just exfoliate it. I guess there's also Xiaodong, and then you can have many crystals like this. Of course, you find by, you can give them a score based on how many values they have, etc. You can find many crystals, many new crystals that have the band minimum at, for example, another point than the K point. And let's take the example of SNSE2. This is the band minimum at the M point. You can clearly see it here. This has low band gap, so it's gateable. And you can do a Moire system out of this, and you can dope it by gate doping. The theory says that as you do the Moire system, you're going to get a flat band, okay? But unlike the flat bands in graphene and MOT2, this flat band is not topological. So you say there's nothing interesting. Well, this is the last slide. That's not true because of this, the way this endpoint works, the way this endpoint twisting works is you have directionality in different directions for different M values. You have 3 endpoints. So you have directionality in one direction for one value due to some non-crystalline symmetry that comes out. In the other value, you have directionality in the other direction, in the other direction. So then, when you go below the charge gap, you basically have a TJ model. So this is a quantum simulator for one-dimensional spin liquids, because the TJ model in one dimension is a spin liquid. Of course, asking how this spin liquids in one dimension are gapless, asking how this gaplessness breaks down by adding longer range hoppings, which are bound to be very small here, is a new question that people are working on. But I wanted to point out that you can get simulators for spin liquids here. So this is my last slide. I hope I convinced you that basically topology is important. We use it in every day. Without it, we couldn't understand, for example, the spectral function of graphene, which has been predicted and recently measured. And we can't really understand this, Moire engineering. But I also wanted to point out that there is a problem, and the problem is that there's about at least 500 exfoliable materials, meaning either have been exfoliated, which are around 200, or materials that exist in the bulk and are van der Waals, and those for sure will be able to be exfoliated. And then you've got 500 materials, so that means you can put hetero, homo bilayers, you can put 2 layers, 3 layers, 4 layers, and then you can twist the angles of each of one of these layers. Okay, so then you can ask, well, what are we going to do? We want the phase diagram of such a system, but the angle is continuous, for example. So one of those calculations where I showed you that the band structure becomes flat, so you go from large angle to small angle, takes about 6 months to do correctly because you have relaxation. So you obviously cannot do 6 months for each and one of these infinite possibilities. So now this is obviously just pulling this out of the pocket, but hopefully AI can help with calculating this because otherwise we cannot. So this Moire work was done by Dumitru, Jonah, and How Are You? But in the theory department, the DMFT was done by Gautam Ray and Lorenzo Kripa in the groups of Giorgio, Roser, and Tim and Antoine. So with that, I thank you. Oh, and the experiments were done by Dmitry Effetov and more recently Eva Andrei and Stefan Nash-Berger they were collaborating with. So thank you very much for your attention. For a true flat band of charged electrons, the first thing, if it's exactly flat and you're at integer electron number, you just ferromagnetize. That's an exact solution. The reason for it is, so now for fractional filling, then you could have different things. But for the integer filling, where I have, say I have a band, I have exactly 2 flat bands of, spin up and down, right? If I sit right in between them, or if I put my fermion of 1 electron, and put a repulsive interaction, then what you want, your repulsive interaction, you have no kinetic energy. So any repulsive interaction is going to be a positive semi-definite operator, meaning it's going to look like this, where this can be either the electron number or the electron. So then what you want is to find a 0 energy ground state that, since the positive semi-definite operator, will be exactly the ground state. So you can prove that there's an exact solution where it just does this. So flat bands like to ferromagnetize under repulsive interactions. Now, you can ask, what's the spin wave dispersion around it, and that will get into very complicated things. The spin wave can be stiff or non-stiff, depending on whether this band is trivial or non-trivial. But at fractional filling, then it could be many things, including a Wigner crystal. Hartree-Fock, for example, could give you Wigner crystals, but Hartree-Fock is usually wrong. So flat bands, we can get into this later, but basically flat bands, Hartree-Fock is much worse for flat bands than for non-flat bands. So all the Hartree-Fock Wigner crystal solutions that you have are likely to be wrong, and this is part of the reason why in this pentalayer graphene, there's been a lot of air got sucked out by people predicting anomalous Hall crystals, which are Wigner crystals, which just don't show up, because so Wigner crystal is kind of hard to predict, as you know. Probably the question probably no. So I don't know what will show up, but certainly at integer electron filling, you get ferromagnets, because it's just very easy for the band to ferromagnetize. Yeah, that's a very good question also. So it's hard to, so basically, yeah, so the main answer is I don't know fully. But what I would think is, obviously things like disorder, etc., etc. But then the reason why this is so clean is basically you just have the same layer on top of each other, and you don't have any of these atoms creating extra chemistry around. So I think the moment you add extra chemistry, you get issues. So I don't know, but periodic arrangement of them, first of all, it's a problem. If you don't get periodic arrangement, then you probably are going to get some localization. You need the mean free path. Part of the reason why this works is the mean free path is so large, so it's much larger than the Moire cell. Otherwise, you'd get localized. Otherwise, this Moire would act as a localization potential. But here, the mean free path of graphene is huge, much larger than the Moire unit cell. So I think potentially it could work. I never say never, obviously. So I just don't know. I just don't know if you can reach the same level of cleanliness as in these samples.
I have a quick question. So for your Anderson model with the where you have this gamma point, is this made by sort of guessing what the right atomic limit degree of freedom is to project onto, or is there like a algorithmic way of generating this given a slightly more complicated structure?
That's very good. So here, so the logic went like this, right? So we knew the band structures of this Mr. McDonald, right? So we knew this, and we knew the eigenvalues. So then you ask, where can I get to with the Coulomb interaction? The Coulomb interaction is around 50. Whatever, 40 to 50. So then you put a window, which is also your Varnairization window, really. And then you say, oh, in this window, can I borrow, right? So these bands don't have the correct representation to give you an atomic limit. But within this window, you can say, can I borrow these representations? And in fact, if you just swap one of them here, that's the atomic limit. So there always is, there's an algorithmic way of doing it, which is you look within the Hubbard U, you ask, what are all, you see, within the Hubbard U, I don't have this band. These ones cannot matter here because, first of all, they're outside of the Hubbard U range. Also, exchanging, so also, the further you are, right, there's no Berry phase because the Berry phase gets large. So I know if I have a large band gap at some K point, I can't have any Berry phase there for the flat band. So that's why these are flat here, right? So that's why they're heavy here. Heavy means no Berry phase. So most of the time, this is just really the inversion principle. The inversion principle tells you that where you invert it, you got the most of the Berry phase. Everything else, the band can be localized. So you can always kind of pawn off the topology on something else. And here, you don't need to, you can just do it algorithmically. You ask, in this energy window, which is Hubbard U, or Coulomb, how can I create a trivial band with these eigenvalues? And there's only one way. In some other cases, there might be more than one way, in which you have to test which one is the most localized, because they will give you the nicest Coulomb. All you want to do is put the Coulomb into the least amount of degrees of freedom that you want. So that's the algorithmic way.
Actually, I had a question about this as well. So in this picture, right, all of your Berry curvature would be kind of concentrated in one part of this flat band. So are you kind of in a hand wavy way? Are you always fighting that if you want to get FCIs?
Yeah. Well, so that's a very good question also. So here, in graphene, right, at the beginning of graphene, there were models that were being made where basically people were banging on about the Dirac point. There's no Berry curvature at the Dirac point. If you plot the Berry curvature, I mean, it's not really Berry curvature, it's a non-abelian version of it because they have C to T symmetry, but whatever. It's all here. And it's obvious that it has to be here because that's where the gap is the smallest. So there's no, so this type of Heavy-fermion description where most of the band is trivial has to be correct when gaps are small and you have the separation of scale. Small gaps where there's most Berry curvature, large gaps where there's no Berry curvature. Now, as you say, for FCIs, there's, of course, it's, if you have a flatter Berry curvature, you're more likely to get FCI. But we don't really know. The FCI is kind of a weird thing, despite a lot of, right? It's not that it's necessary to have flat Berry curvature, right? As you know, basically, you can have FCIs even with Berry curvature that's localized numerically, and we don't know, right? So it's not a necessary condition. So I don't know how to, and certainly in this case, you're right, you don't get FCIs in TBG, even by calculating them, whereas you get in MOT2, etc. But for example, in pentalayer graphene, where actually if you just do the Hartree-Fock, the Berry curvature is very concentrated. Of course, I don't expect the Hartree-Fock to be correct, but you do get FCIs. They're quite strong, and nobody knows why they're so strong. So I think from getting a microscopic description of the FCI that has predictive power, we're very far away from that in real. Like, for example, we don't understand pentalayers. So it could be, as you say, it's probably likely that you don't get FCI here because the Berry curvature is concentrated here. But I wouldn't put my hand in oil, burning oil, that in other systems where I do have Berry curvature is concentrated, you don't get FCI, because we know, at least in tight binding, we have models where you can. So that's a tricky situation there. Thanks. Oh,
Very naive question. What?
It's supposed to be thrown.
Okay.
Oh, really?
But looking at the dispersive band, I think they look a bit like Rashba splitted bands.
Yeah.
So is there something?
Yeah, very good. So the dispersive band, not only do they look like Rashba splitted, so it's very good. So if you do, this system has some symmetry, and then the form of the Hamiltonian here is literally just given by symmetry. So K dot P Hamiltonian is given by symmetry. Now, there's two things that you notice. As you notice very clearly, it looks like there's some splitting. Also, this velocity is actually the Dirac velocity of graphene, basically. So once you get, so the reason is that when you go to this, what you're doing is you're taking, this is the Dirac node of the upper layer, right? So you're basically taking two layers and twisting them. Then you're going to have a Dirac node of the lower layer here, right, which is right above. I'm going to draw it right here. Okay, at the gamma point, which is where you want it, you have degeneracy. If I just plot them on top of each other without breaking them, I have Dirac nodes coming from 1, 2, 3 points, and another 1, 2, 3. So I'm going to get a 6-fold degeneracy here. Okay, and now I'm going to add coupling in between layers. So this 6-fold degeneracy breaks by coupling in between layers, and you get a 1-fold, a 2-fold, so there's a 6-fold. It breaks like this: 2-fold, 1-fold. There's another bonding and anti-bonding. This is the one that came down. This one is this one is this one, and then you just get some splitting here. But it doesn't have to do with spin-orbit coupling. This is all orbital splitting. There's no spin splitting there. It looks like Rashba though.
Right, and I just want to point out that so these are not the right, this is astronomical coupling. So Rashba, you don't need rotation symmetry, and simply kind of weighing it right down, it's going to look like a Rashba and looks like
Yeah.
There's some rotation symmetry that's giving you this degeneracy here, and there's an orbital temperature that has been affected.
Yeah, it's all orbital. There's no spin. Although it has, as Ben says, it has exactly the same form as the Rashba, but it's just.
Concerning the degeneracies at gamma and at k, especially at k, if you have an electric field that is perpendicular to your bilayer, okay, you keep the order 6 or the order 3 rotation, but you lose all the order 2 rotation along the plane, and in some cases, and not some other ones, you have you no longer have degeneracies at k.
I think with an electric field that's perpendicular.
Without electric field, it's always degenerated, I agree.
I think with an electric field that's perpendicular to K, to the field, I think if it's parallel, then, but with the one that's so these degeneracies are protected by C2Z times time reversal. There's two symmetries that protect them. Well, they're always protected by this, but they're pinned. There's an exact degeneracy here, okay, as you said. Now there's almost a degeneracy here, which is the reason why the K point is not really the most important point here. All the curvature. Okay? So these are the symmetries. C3 pins it at the corner. This protects Diracs in 2 dimensions and leaves valley invariant, which is important here because you're in the same valley. Now, if I had an electric field like this, this keeps both of these symmetries. So they one split your Dirac node here, right? It keeps a field like this. C2Z does this. T electric field is invariant. C3 is invariant. Now, if I put it somewhere, so if I put it parallel, then it might do something or have any parallel component. But if I just put it up, it won't do it. That's a good point. It might split the bands, but the K point will still be invariant.
I want to know about the superconducting state, actually. Is there a consensus on the symmetry of the other parameter? Do we have anything to say about the mechanism?
Yeah, I mean, I have some slides on it. So as you obviously know very well, that's this hill of every. It's just that the you just have to. It's hard to predict. So basically, what the experiment does tell you roughly is that it's a triplet, at least in trilayers. Okay, like in bilayers, but let's say in bilayers also. Twisted trilayers, which are just square root of 2. They're basically. There's the same thing as this. in the mirror symmetric ones. So it tells you it's a triplet, which can be interpreted as either spin triplet or valley triplet. And it tells you that most of it is gapless, in the sense that some people, like Stefan, see a transition between gapless and gapped, whereas Ali sees gapless. Okay, I think Andrei also sees gapless. So let's say it's gapless and spin triplet. You can get this with the Heavy-fermion theory. Okay, you can get this to be the lowest state. Now, as you know, there's many other states that are very competitive. For example, in some limit, this system has some U4 symmetry, which makes the gapless states, or although a lot of them be the same energy. And then, you know, which one you split. So you can say, oh, we can match it, but I wouldn't call this a prediction. But you know, you can certainly get here just because there's topology in this guy. So the story here is, of course, as you know, it would be basically there's a pseudo gap in this system, which would be the pairing on site of the heavy fermions, and then there's a gap which would be the phase coherence is given by the C electrons, etc. So you can get the gapless triplet. In fact, the triplet is almost always favored in this, but you know, I wouldn't say that. I wouldn't come in front of an audience and say that that's a prediction, just because the energy scales around it are so small that just by changing the parameters a little bit, I could get something else, I think.
Okay. Well, let's thank Andrei again.